Was the last picture in the homework supposed to be series?
Yes. All right, ladies and gentlemen, let's begin some material on 9.5, which is on series. And it is true, like you just pointed out, on the homework, the very last question actually asked you to add up some things. And the only resource you had was like to do that by hand, and that was really annoying. So today we want to introduce a technique for summing that in a little bit of a quicker way, come up with some tools to sum up sequences. Along the way, we'll talk about, maybe we'll come up with a rule for arithmetic and geometric series, and also talk about summation notation along the way. And before we really say anything else about a series, we should just note that like this, you guys, is a sequence. That's what we studied on Monday. And this is a series, and the difference is, of course, that in the second case, we're adding them up, right? So series should mean, in your mind, sum, okay? It makes sense to it makes sense, for example, in English to say, evaluate this series. Perfectly good, grammatically correct English sentence. It makes no sense, though, to say evaluate this sequence. That doesn't compute. Okay? So series is completely and utterly the same as the word sum for a mathematician. In English, you probably use those words interchangeably. So if we're going to talk about sums and adding things up, we better have a nice, compact notation for that. And we've already thrown this at you a little bit. Just exposed you to it in this class even, and maybe before you've seen this as well. We use a capital sigma. In the last stat unit, you're accustomed to the lowercase sigma. So this is an uppercase sigma, and from the Greek alphabet also. And that's a good letter for it, because sigma has the sound like s also, and we're thinking about sums here. So it's like, sum begins with sigma, right? Every letter makes a sound. Sigma says s. Okay. So have we done summation notation a little bit? Well, I don't know. Let's go through and really be clear about what the things are that are appearing here. Over here, this is, guys, the explicit rule. Right now it looks really simple, but in practice, when we look at some of these, that rule could be something very complicated, but it's never the recursive rule, right? It's always the explicit rule. In this case, some function of k. In this case, k is our index variable. And we let that index variable go from some minimum value inclusive of that minimum value. We'll call it k0 here, all the way up to the maximum value of k, which we'll call n. Yeah.
Is the dot just a period? Or
yeah, it's a period.
Oh, okay.
This is a sentence that begins here and ends here. So let's try evaluating some simple ones here, and then we'll see. By the way, the limits of summation can either appear up on the bottom and top, or to the right of the sum too, depending on space and style constraints. Yeah, as well. Right. So this is the sum of all the terms ak running from k0 to n. So here we have our minimum k value is 1 and our maximum k value is 6. So in the end, these should come out to be a number. Like when we're done with this, you're going to give me a number. There isn't going to be a variable involved in the end. So this is, again, this is the explicit rule. By the way, that's the explicit rule for what kind of series or what kind of sequence would you call that 2k? Careful, I told you that the thing that goes in there is the explicit rule. I mean, let's start writing it out and it'll be clear. The first term is if you plug 1 in, 2, that's if k is 1. And then if k is 2, 4, if k is 3, 6, etc. So tell me what you get when you add those up. And then down below, what are we doing? We're starting with, what's the very first thing I'm writing? Yeah, 16, or the first thing, which is 4, we're using the first index for us, will be k equals 4. So we're going to write 4 squared, or 16, plus 5 squared, plus 6 squared, plus 7 squared. And then in the end, just tell me what each of these equals, right? Do you understand that at the end we get a number? And it will represent the sum of all the terms that we just talked about. And is this arithmetic or geometric, by the way? The first one was arithmetic. If that wasn't, it is not clear now. Each piece goes up by 2. What's the second one? It is neither. Sorry, that was a trick question. Okay. Not every sequence has to be one or the other. In fact, in general, we don't necessarily have either one, right? So, what's the first sum?
42.
And the second? Someone confirm those, and then we'll be good. Are we good at adding those up? Does that make sense? One thing I want to make clear, because you guys will make this mistake, I know you will, is if you're writing this in summation notation, I see a lot of people who take this sum, and if you're writing this in summation notation, don't be this person. Well, the sum starts with 16 and goes to 49. I hear what you're saying, but that is not how we use summation notation. We always start with the first and last index, not the first and last term on the top and bottom of the sum, right? Does that make sense? This is the explicit rule. This is the first and last index. Just want to make sure that's clear. Okay? Here are just a couple properties that we can use to our advantage when we're thinking about sums and working with things in summation notation. Here's one that might even apply to the first example on the last slide. If you ever have a rule that has a constant multiple in it, then you can pull that constant multiple out. That's what this says. And you can do this sum and then afterward multiply by c. So for example, in A on the last slide, we had the sum 2k, right? And now what I'm saying is maybe you could have done this instead. Do you agree? What was it? You could have done, instead of doing 2 plus 4 plus 6 plus 8 plus 10 plus 12, you could have done 1 plus 2 plus 3 plus 4 plus 5 plus 6. And then afterward multiply by 2. You understand we can like factor out the 2. And that might quicken your work a little bit on certain, or you might make things a little easier in certain cases. So, and that can be proved pretty quickly just using like a set of parentheses. It's just the distributive law, really. Here's another property which, again, can kind of maybe be proved from the first principles of arithmetic that this would be the case. This is saying that, for example, the sum of k plus k squared or something is equal to the sum of k plus the sum of k squared. Right? For example. And again, just think about actually writing these sums out, right? It would just be you, instead of thinking about like this thing, k plus k squared, it'd be take all the first parts, add them up, and take all the second parts and add them up. And addition is commutative and associative, and so forth. So it's going to be great. So those are two properties. Here's a third property I think is interesting. This should say plus c up here. I might call this like the re-indexing property. This means that you can rewrite a sum using any set of indices that you like, provided that the sum is still the same. You and me, we're cool. Like as long as the sum is still the same. So for example, on the one that we were doing earlier, what is it, k squared from k equals 4 to 7 or whatever? That's the same as like k equals 0 to, what would I have to go to here? 3 of k plus 4 squared. Can you verify that those two sums are actually the same sum? All you have to do to check that I'm right is to like start plugging in values. Don't you get the same, like actually expand this out, and you'll see that we're calculating the same sum, aren't we? So that's kind of a fun little trick. And there are lots of other cool properties of summation that we can look at if you want. You can go play around. I just linked to some website you can do. But I just want to give you a couple so we have like a little bit of a sandbox. Yeah. So you could go up or down on these too, right? You could make all these indices go up by 10. You could go from like k equals 14 to 17. And then this would have to be, instead of k squared, if these go up by 10, this has to go down by 10, right? So that would be another good way to write it too. Let's do that one. From k equals 14 to 17, k minus 10 squared. That's kind of fun, right? The point is we can like play around with these as like robust algebraic objects. And it would be good to like know our way around the territory. Okay, so you're just using these properties. Let's answer these questions here. The first example, I think you'll like using the first two rules together to answer. And the second one is the second property. The third property, rather. Notice here that I'm not telling you what the sequence xn is. I have no idea what the terms of that sequence are. I'm just telling you that, hey, I have this sequence. I'm not telling you what it is that's inside my black box. When I've added my terms up, though, from 10 to 100, I get 5. And I have another series in a black box that you don't know anything about, except that when I add up the terms from 10, 11, all the way up to 100, I get negative 2. By the way, is that possible? How do we get negative 2 in the sum? Is that? I mean, it's possible if the terms themselves, some of them are negative, right? Then that's okay. Maybe they're all negative. I don't know. Some are by negative, some are positive. Yeah, so there's not much work to do here, right? Though I would insist that we like think through the properties we're using here. This is equivalent to 2 times this series minus 5 times this series.
And you just plug them in.
And then you can plug them in. What is this? This is negative 2. And this is 5. So whatever that equals. Okay. And down here I'm asking you to re-index this series. So that is, I'd like you to start with k equals 5 and rewrite the sum where k equals 5 is the first index. And you still haven't changed the sum. That's the point. Is please don't change the sum. Just rewrite it so that it starts with k equals negative 2 over here. So what are we going to put as the top limit, and what are we going to rewrite the explicit rule as in order to make this happen is the question. Yeah.
So I'm assuming that the variable k equivalent is not a constant, or you're not going to use it? Like the letter k, you don't even need to use the letter k.
There's nothing special about k. Yeah, we like letters close to the center of the alphabet. We like k. We also like I and j. We love n and m. All those make like good indices for sums and sequences and stuff like that when we are referring to the mth term or the kth term or the. So, all right, so what would the top limit be here? If we change the bottom limit from 0 to 5, the top limit is going to change from 25 to 30. And then what about the actual explicit rule here? How's that going to change? I need it still to be true that plugging in 5 to whatever I have here gives me the same thing as plugging 0 into the original thing. So what do I need to adjust the rule on the numerator?
Subtract 5.
Yeah, I need to subtract 5 from the k's here. So on the top that'll just be k then. And on the bottom it'll be 2 to the k minus 5 and k minus 5. Factorial. So do you agree that you don't even have to, we're not even asking you to evaluate this sum necessarily. I'm just asking, is this the same sum? I think it is, and a quick way to verify that would be, if you plug in 5, 6, 7, etc. to this, are you getting the same terms as if you plug 0, 1, 2, etc. into this? Try it. Maybe try 30 as well. If you plug 30 into this, is that the same thing as when you plug 25 into this? Should feel exactly the same, I hope. Okay? Could we re-index back down to negative 2 as well? Sure, I don't know. What would the top limit be then? What's the top limit going to be? 23, okay. And then what's going on over here? Yeah, I want to do everything, all the k's here, plus what? Everything is plus 7? Oh, okay, I hear you. Again, verify that that works. Just go through and check. Is this really giving me the same terms? By the way, how many terms are there in this series? Yeah? Okay. Go ahead. You ask your question. All right, how many terms are there in this series? They're the same series, so any one of these. How many terms are in this series? You actually write it all out. How many terms are there we're going to add up? Yeah, it's actually 26, right? So what's the rule in general for figuring out how many terms? From 5 to 30, that's 26?
Well, it depends on where it starts.
Does it though? This is still 26 terms too.
But like,
What do you do?
the bottom one minus the top one.
Or the other way around, but then plus 1, yeah. So yeah, like if your history teacher says you need to read pages 200 through 230 tonight for homework, then how many pages did he assign? He assigned 31 pages, right? Okay. Sorry, are we good, Amy? Still a question?
If you have a negative number factorial,
Thankfully, that's not going to come up here, right?
oh yeah. No, it's just a question.
Yeah, the answer is we don't know what that means for factorial, but we should talk sometime because I can help you out. Okay. Yeah.
So when you re-index, did you, so other than like the indices on the sum, on the actual rule, did you add, for B, add 2 to everywhere there was a K?
Yep. Yep. Yeah, exactly. So if these limits go down by 2, then all of the K's go up by 2. Yeah.
Wait, so what exactly does re-index mean?
Just means re-index it so it's the same sum, just expressed with different indices. Right. All right, let's talk about a sum rule for arithmetic sequences. Okay. And right now, I need to tell. This is like every time this is introduced in anyone's pre-calculus class anywhere in the country, you have to like have story time about Carl. Little Carl. Do you know Carl?
Yeah.
Yeah. Little Carl. Carl Gauss is his last name. And this is a story which is probably false. Okay. So it's told though that he was in his elementary school years, but he's still very little Carl, and he's in his one-room schoolhouse with other even bigger kids. And the teacher, who's, because in these stories he always is a grumpy old man or something like that, who's like, doesn't want to deal with kids and doesn't like kids. He's like, wants to read his newspaper and set the kids to work on a busy work problem, right? That this is going to keep him busy for a while so he can just like have some peace and quiet up in front at his desk. So he asks them all on their slates, because they all have slates. That's just how the stories go, I think. And then one year in schoolhouse, you have a piece of chalk and slate or something. And he asks them to add up the numbers from 1 to 100. And he thinks, well, that'll keep him busy for a while. That is the integers, 1 plus 2 plus 3.
Oh, yeah. Okay, and you added 1 to 100.
So he's like, whatever, he's 7 years old or something, and he immediately comes up with it, and he like drops it on the teacher's desk, like slate drop, I guess, maybe something like that. Boom, and with lots of fanfare there, and the teacher's like puts away his newspaper. He's like, wait, what? That was supposed to keep you busy for a while. And the answer, yeah, how do you get that answer? What did he do? I mean, how did he come up with that so quickly? Because he was right in the end. What's the strategy?
First and last number.
Yeah, so if you're doing 1 to 100, then I think I see what you're saying. 1 to 100 is 101, and then.
The same for each one.
Okay, and how many 101s do we have?
55. No, wait, no.
Why would there be
If you
55?
add the 1 and the 99, you can do that 50 times. But
Right.
you have a 50 in the center, so you have to add.
Do you have a 50 in the center?
No.
Yeah.
Well, if you go from 0 to 100.
No, but we're
Oh,
not
if
going
it's
from 0 to 100.
I think you'll get the same answer if you add 0 to 100 and 1 to 100.
Yeah, same thing.
But like, no, because you say you go from 1 to 99.
Yeah, but you don't have to worry about a 0 if there's a 0.
Yeah. I know. I like the conversation. What's the answer?
No. The 100 will be left unpaired to be 1 plus 99. So then 2 plus 99.
And then add 100 afterward or something?
Yeah.
Okay, you can do that.
So it's like 100. When you do it, you
49 times 2 plus 50.
And then you have to add like 150 afterwards. Okay, I see what you're
Or
saying.
you can go from like 0 to 1.
What's the answer? All right, you'll have to tell me what the answer is at some point, but he was right. So we're going to take a cue from Gauss's book, based on that cute story here, and think about an arithmetic sequence. But we'll do it in general. We're going to be thinking about an arithmetic sequence of any kind, not just the simple one we just considered. So can you just agree with me that this is in fact the series we're looking for? This is A1, the first term. This is A2, the second term, but I've written it as A1 plus D. Is that okay way to write the second term? A1 plus 2D, that's the third term. Is that an okay way to write the third term? All the way up to down here, you okay with this? This is the last term, the nth term. And do you agree in Brown that that is in fact the last term, the nth term? It's just the explicit rule for an arithmetic sequence. So this is in fact one way to write the sum of the first n terms of an arithmetic sequence. There we go. I'm also going to write it backwards down here. Now this one might take a little bit of work to see. But down here we have the last term, and then the second to last term in blue. Do you agree that that's the second to last term? One way of saying the second to last term is we could say the last term minus whatever the common difference is to recover the second to last term. Does that make sense? And the third to last term will be two copies of the common difference subtracted from the last term. All the way down to, this is a really funny way to write the first term, but this is in fact the first term. It's the last term minus n minus 1 copies of d, right, to come all the way back home. And what are we going to do here? Can you see what we're going to do?
Subtract.
Close. We're going to add these together. And when we do, can you already see what's going to happen? Over here we get red plus red is A1 plus AN. What's blue plus blue? Also A1 plus AN. All the way down the line, the D and negative D, or the 2D and the negative 2D, all the way down the line cancel out. How many copies of A1 plus AN do we have? Given the fact that there were as many terms as we said there were. What is it?
S.
There are n copies of that. Now notice, by the way, over here, we didn't mention this, but notice we have 2 copies of the sum, though, don't we? So we need to account for that. And here it is in a box, the rule for the sum of an finite arithmetic sequence of length n. Okay? How are we doing? You like that? Okay. Now I hear you cry. Let me hear it. You want the sum of a... Wouldn't you like to know how to find the sum of a geometric sequence or series? By the way, you don't have to like prove this from first principles every time. I just want to show you where this formula comes from, because you know how we do. Fun times. Okay. You can verify that by that way that works for 1 plus 2 plus all the way up to 100. You can see you get the same answer that we use.
5,050.
It is 5,050. All right, let's look at a geometric sum now. The only thing you really have to have on this slide is the box thing at the end, but I just thought I'd share the proof with you just for fun. Same with the thing I'm just going to show you. I'm going to walk through a proof for geometric sum formula, and the only thing in the end that you really have to have is the box thing at the end. But I thought it would be fun, just kind of like a cinematic thing, to kind of your entertainment for the day, really. Thinking about the sum of a finite geometric sequence also. So let's do a similar thing we did on the last slide. Let's write out the sum. And the sum is the first term, A1, plus the second term, which, or just like the last one, we're expressing as A1R. Is that okay? And the third term will be A1R squared, etc. All the way up to the nth term, which is A1R to the n minus 1, which is just the explicit rule in Brown for the nth term of a geometric sequence. Do you agree that that's the sum we're looking for? I hope so, but does that make sense? All right, now this time we're going to take a little bit of a slightly different approach. I'm also going to consider the sum times r. Everything on both sides of this equation times r. And this is the result of having done that. Do you agree? If you multiply every single thing by r, a1 times r is a1r. a1r times r is a1r squared, etc. And s times r is rs. So everything in this top equation just gets an extra r. And then what do you see what I'm going to, I've already kind of color coded to make it, maybe I'm going to give it away here, but yeah, I am going to subtract those two. And when I subtract, I get, on the left, I get s minus rs. And everywhere else, the reds and the blues and etc., they all cancel out if we subtract. And all that's left on the right side is a1 minus a1r to the n. And what is our goal again? Oh yeah, that's right, it's to solve for s. We'd like the sum. So we can factor that out on the left side. And divide by 1 minus r, and we have our rule. Is that beautiful, or what? Tricky, tricky stuff. Okay. So there it is in all its glory. a1 times 1 minus r to the n over 1 minus r. And now we'd like to do one last slide with an example on here if we can in the last 2 minutes. Yeah. Oh, I haven't put anything for this unit up yet, have I? Yeah, you're right. I'm on it. Okay.
Will it be on it because there's a little bit on it?
Let's find the sum from 1 to 6 of 2k. Wait now, this sounds familiar. S6 is what we'll call it. How about the sum of the first 6 terms? This sounds familiar, doesn't it? Did we do this one already? Maybe we did. The answer was 42, right? All right, let's see if we get 42. What kind of series is this? We already said it earlier today. I'm just testing you. Yeah, it's arithmetic, right? Because if you write out the terms, you'll see. But you could even write this as in the normal arithmetic sum formula thing. It's pretty clear, I think, from the form, even from the explicit form given, that it's the common differences too. All right, so that being said, what do we need for the arithmetic sum formula? We need, look at the box. We need an n, which is here 6. We need a1 and we need an, or a6 in this case, right? So n is 6. a1 is, what is a1 and what's a6? 2 and 12. All right, so tell me, do you get 42?
Yes.
Hopefully. All right. So that's cool. We'll go back and try that theater problem. What do we need for the geometric sum formula? We need a1, r, and n. I guess we're done. That's sad, but okay. See ya. Have fun on homework 2 tonight. You'll do great.